Hey class, so I wanted to make a video here for this last problem on the Wiley assignment. It's a little bit of a tricky one, and I'm going to go ahead and start by apologizing for my poor handwriting. I left my Apple Pencil in my office, so I'm doing this with my finger, so we'll see how this goes. But anyway, we have this situation where we have kind of this initial situation here where the ball, there's like this ball going around in a circle on a horizontal table that like has a hole through it. So like the string kind of goes down into the table and there's a hole through which you can pull it to apply tension. So that little hole that I'm talking about, would be sort of right here in the very middle of these tables. And as you start to pull down, the tension in the string is going to increase and the ball is going to start to rotate faster. And you'll eventually pull so hard that the string can no longer handle the increased tension and will eventually break at 160 newtons. And so the question is asking us, how fast is it rotating at that point? So this is a bit of a tricky one for sure. So if we first start, I immediately am thinking something going around in its circle, it's got a force acting on it, and there must be somehow involved uniform circular motion. And so if I think about it as it's going around in a circle, it must be experiencing a net force that's equal to its mv squared over r, its centripetal force. And that centripetal force is really just being applied by the tension. So the tension is going to be equal to mv squared over r. Keeping in mind, this is in the final situation. This is after it's been pulled down because that's when it's about to break. So this T here is the maximum tension of 160 newtons, and this R, maybe I'll call RF, the final radius when it's down, the radius which we're solving for. So in this problem then, I could go ahead and observe that what we're given is information not about the changing velocity, but thinking more in terms of angular velocity. So I know that for something moving in a circular manner like this, v is going to equal omega times r. And the reason that I want to go and look at omega is because as this moves inward, it's in an isolated system. It's free of outside torques and frictions. So therefore, I know that angular momentum is going to be conserved. So I'm going to use the idea, I'm going to go ahead and scroll down to make some more space. I'm going to be using the idea eventually that the angular momentum initial, L initial, equals the angular momentum final. So really the I of the system when it's in the initial situation times the omega in the initial situation, which is given to us, is going to be equal to the I final multiplied by the omega final. All right, so this here, if I plug in omega times r for v, that will enable me to get an equation for omega final, since this again is the tension and the r after you've reduced it in size. So if I plug that in, I'll get T equals m, and then v squared becomes omega squared times r squared, but it's still divided by r, so one of those r's cancel, so I really just get T equals m omega squared over r, or since I'm running out of space, I'll write it off to the side here. If I solve that for omega, I'll find that omega, again, this is the omega final, just so we're not confused. The omega is going to be equal to the square root of the tension T divided by m times r final. So the cool thing is that's our omega final. Omega initial is given to us in the problem statement, so we can put this all together in our conservation of angular momentum equation. I for this ball is just a point mass, so that's just going to be equal to m r initial squared omega initial, which is given to us, and that's going to equal m r final squared, the inertia for the point mass again, times omega final, which is my square root of the T, the tension, over m r final. So we can see our m's are going to cancel here, and now r final is the only thing we don't know. We're going to have to do a bit of tricky algebra because we have r final here and r final here. So just as a hint, maybe I'll just tell you the first thing you're going to want to do is actually square everything in your problem statement to get rid of this square root. So you get r initial squared squared, so that's r initial to the fourth, omega initial squared equals, now this r final squared is also squared, so that's r final to the fourth, and now our omega final from before is squared, so that gets rid of the square root, so we have t over m r final. So you can cancel out this r final with one of these, making that a 3, and then solve for r final, but you'll have to do a cube root, so get excited for that. Anyway, that's a kind of a tricky problem here, and I wanted to sort of help you all get set up and trying to solve. So again, I hope this helps as we start looking at this problem, jumping in to the ideas of circular motion and centripetal acceleration, and using that in combination with conservation of angular momentum. All right, well, go ahead and solve, and I hope you get a box-worthy answer.